Okay, we just came from the previous first part of this problem where we were given g of x and we restrict the domain from 0 to 2 pi and we're asked to find the local min and local max. We found the critical numbers and we divided the number line with those critical numbers. Now we're trying to find positive or negative sign in each of these regions that we divided the number line into. There's 3 regions. And to find these, we're going to have to consider the locations of the x values for which g prime of x is positive and negative. And it's tricky because this was a trigonometric equation. So what we did is we started in the last note by setting g prime of x greater than 0 and solving for the trig function. We got cosine x is greater than negative 1/2. So what that means is on the graph of the cosine function, the values of x that make cosine of x greater than negative 1/2 will be the values of x for which g prime of x is greater than 0. Now that was step 3 in the last video for this problem. So I've drawn this graph. I've got y equals cosine x, and on the x-axis I marked my restricted domain from 0 to 2 pi, and I marked my critical numbers. Okay, and what I did was on the y-axis I was interested in y values between negative 1/2 and 1 because those are the values that will make the cosine, in other words, I should say it is the area where the cosine of x is above, greater than negative 1/2. Now down below you see the bracket. I have the cosine of x will be less than negative 1/2. In other words, it's going to be between negative 1 and negative 1/2. That happens when y is between negative 1 and negative 1/2. Okay, so what I'm interested in is finding the marks of positive or negative values for the divvied up number line that I have in step 3. So let's continue from this point. We have g prime of x equal to a negative in this region here, which is for x values between 2 pi over 3 and 4 pi over 3. And then we have g prime of x equal to a positive here in the region to the left and right of that, from 0 to 2 pi over 3 and from 4 pi over 3 to 2 pi. All right, now I'm reviewing your whole trig class here, so if you're rusty on this, you go back and look it up in your trig books. I don't want to reteach you trig, so you go back and review this. Thus, for our sine graph, we have the g prime of x is going to be positive to the left of 2 pi over 3, so we have a positive slope leaning to the right for the tangent. And then between 2 pi over 3 and 4 pi over 3, we have the slope negative. So the slope of the tangent is negative, it's leaning to the left. And to the right of 4 pi over 3, our slope is positive again, so our tangent's leaning to the right. Okay, so that means we have a change in the signs of the derivative on the left and right of 2 pi over 3. It went from positive to negative. And we have a similar thing happening at 4 pi over 3 where we went from negative slope to positive slope. And you can just look at the picture and see what that indicates. It indicates that we're increasing from the x interval from 0 to 2 pi over 3 and from 4 pi over 3 to 2 pi. And the function's decreasing on the interval from 2 pi over 3 to 4 pi over 3. So those are our intervals of x values of increase and decrease. Now let's make our final conclusion about the local min and local max. We know that the function g is continuous for all x on the real numbers. And that implies by the first derivative test that we have a local max value at g of 2 pi over 3 because we changed signs there. Okay, we changed signs from the slope from positive to negative, so that means we have a local max at g of 2 pi over 3 equals 2 pi over 3 plus square root of 3. So write it as an ordered pair, 2 pi over 3 comma 2 pi over 3 plus square root of 3. That's xy. And over on the other side we have a local minimum value at 4 pi over 3. I should say a local minimum number. Evaluate the function to get the minimum value. G of 4 pi over 3 is 4 pi over 3 minus square root of 3. So we have the ordered pair. Xy equals 4 pi over 3 comma 4 pi over 3 minus the square root of 3. So we were able to use the first derivative test to find our local min and our local max. This is a tough problem. And, we just have to get into it, figure it out, tear it apart. We might not have enough time to do something this tough on the test, but this is a really good exercise if you are going to be a serious mathematician.